and welcome back to another lecture of Statistics 479 Time Series Analysis. So we already talked about how to estimate terms, or that is parameters, for the AR autoregressive process. But we typically want to know not just what the terms are, but where is the process going. That's forecasting. That's what we're doing today. So we're going to look at forecasting for the autoregressive process. In this case, we're really not even going to assume that we have an autoregressive process. We're just going to have to try to use the data that we have to predict the future. Can we do it, or is it not going to work? Well, that really depends on the data we have. So what we're going to do is take a deeper look at that in today's lecture. It's going to be very similar in the sense that we have to solve a big linear system of equations. And this one is really big, not like the Yule-Walker. It's really big, and we're going to have to figure out how to deal with that. So let's jump into the notes. And welcome back to another lecture of Statistics 479 Time Series Analysis. Today we're going to continue what we were doing in the last lecture, which was looking at the autoregressive process, specifically how to estimate coefficients for the autoregressive process, because we're finally at the point in the course where we're going to estimate things like a true statistician. Now, in the last lecture, what we did was we discussed two different ways to estimate the coefficients. We had the Yule-Walker equations, which was a linear system of equations that we were able to solve to get the coefficients. Then we looked at maximum likelihood. Now, maximum likelihood, we assume that we have Gaussian white noise that's kind of underlying the time series process. It's a reasonable assumption since a lot of times noise is actually Gaussian, but it is key to remember that we are strictly making that Gaussian assumption when we do maximum likelihood estimation, because we have a whole lot of normal distributions. So what we did last time was we looked at the joint distribution of our data. And that led to something called the unconditional sum of squares, which led to a nonlinear optimization problem, which is hard to solve. I mean, okay, a computer can probably do it, but we can't get a nice closed form. And it's nice to have a nice closed form. I mean, the Yule-Walker equation was the Yule-Walker equations give a nice linear system to solve. So instead, we looked into the idea of the conditional sum of squares, where we condition on the first data point to kind of account for that weird boundary condition. And then, this is all for the AR1, by the way. If it's for an ARP, we'd have to condition on the first P, which we'll talk about later. But in that case, we had a linear problem that we had to optimize, and we could find a solution. And what we found was that the MLE and the Yule-Walker equations gave almost the same thing, but slightly different. The MLE and the Yule-Walker equations behave a little bit differently around the boundary. So then that leads to the question of, well, what should we actually use to estimate our autoregressive model? And that's why we're going to start in RStudio today to actually look to see what the AR function does. And it's always a good day when we get to start in RStudio rather than writing lecture notes. So let's get into RStudio and see what this is all about. All right, so we are in RStudio now. And the main thing we're going to be looking at is the AR function, which is available just in the stats, the standard package that comes with R. Now, well, let's just see what happens when we run it, right? First, what we need is some random data. And as it was pointed out to me by one of you listeners at home, it would be really nice if we could set the random seed first, so that when you go home and try it yourself, you get the exact same results that I do. So we're going to do that this time. And we'll set the seed to be 479, because why not, you know? Okay, so now that we've set our random seed, let's generate some data. First, I want a white noise process because I love having a white noise process, and we'll get 500 standard normal random variables. There's my Gaussian white noise right there. Now what I'd like to do is use the think it's ARIMA. Yeah, ARIMA sim. So I need to double check the notation for this to make sure I do it correctly. Yes, so what we're going to do is we're going to simulate an AR1 process. I think doing it with this function is probably better than in the previous lectures when I used the filter command, because the filter command, well, it throws around some NAs because of the way it works, whereas this will just kind of clean up everything for us. So what do we need? Well, we need a model, which is a list component with AR and or MA. Okay, so what we need is model is equal to list, and then we're just going to do an AR piece for the first one. So let's see if they have an example, just to make sure that I type this in correctly. Yeah, see, we're going to do AR, we're going to pick some coefficients, and we're not going to do MA just yet. But don't worry, we will. Okay, so going back to the top, we're just going to do 0.7 like we did last time. So pretty simple AR order 1 process. And we're going to, let's see, what else do I need? I think somewhere there is a standard deviation. I'm pretty sure I saw that down here, SD, which is not part of the list object. The list here, yeah, is just for the, okay. I'm not sure what the default is. It's probably 1 because it's always 1, but, oh, I see what it's doing, sorry. What it's doing is it's generating the innovations, which is basically the noise, but we haven't talked about innovation yet, with R norm, and then presumably you can throw in extra arguments that you would pass to functions like R norm, like mean, and specifically the standard deviation, because you wouldn't really want a non-zero mean. But that means we can skip that. But just for the sake of accuracy, I will just put that in there, even though it defaults. Oh, yes, and we also have to tell it how many we want. So we'll stick with 500. That should give us enough to work with without going overkill. All right, so there's our AR1. And while we're at it, let's just create an MA1 with the exact same coefficient of 0.7. So we're going to switch this to MA and hit it again. And while we're at it, let's pick a more complex AR process. Like, let's see, we can have our 0.7, maybe minus 0.4, and plus 0.2, which probably is is causal, a causal linear process. I hope it is. I guess we can plot it just to make sure it looks reasonable. Yep, that looks reasonable. If I got it wrong, it would probably blow up anyway. So that's always a good quick check to make sure I didn't do anything that wrong. And lastly, let's do an ARMA. Oh, I don't know. How about 1, 1? We'll just put together the AR piece with a 0.7 and the MA piece with a 0.7. And this should give us lots of different time series to look at. Now remember, so far we're just going to do estimation for AR processes, so we want to see what happens if we try to fit an AR model to our data when it's not an AR process. That's another thing we want to learn about. Okay, so now why don't we look at all our time series? So we have MF call, MF row is 2, 2, and let's just plot them. We have the AR1, and it looks like that. Okay, cool. We've got the MA1, and it looks like that. Okay, also cool. Kind of looks similar, at least from our eyes, right? Though I guess it does have a little bit different. The AR1 almost is starting to tend towards a random walk as the coefficient gets bigger, whereas the MA1 doesn't do that. What else did we have? We had an AR3 process, which I already plotted, but we'll plot it again in the big grid. And we had an ARMA 1, 1. And we get something that looks like that. Cool. So at least the ARMA 1-1 looks a little almost emaciated in the sense that it's kind of like dancing around a bit, a little bit thinner than the other ones. The other ones look like good, hearty noise processes, except maybe AR1's on the fence. Anyway, now that we've done that, well, let's go back and look. The point I guess I wanted to make by plotting them is when you just plot them, it's not obvious what's going on, right? They all look pretty noisy, but just by staring at it, I can't tell what processes it is. Maybe some brilliant person who does a lot of financial analysis and stares at time series 24/7 can identify it, but I can't. So we're going to use a function to figure it out for us. Now, going back to the AR function, well, we see a couple things. In R, if you see this ... what it's telling you is that there are lots of different versions of the same function. And you might see YW and remember, Yule Walker. Berg, I don't think we know what Berg is, but then effectively the idea is that you can take the AR function and you can specify the method, and it will kind of jump into one of these other methods. So we see Yule Walker, that's the default. That's pretty good because that's the one we learned about. Then there's something called Berg, OLS, which is probably ordinary least squares because it's statistics. We have MLE, and then we have YW, which I assume is also just an alternative way to specify Yule Walker and nothing actually different. But let's go look at the method. Yeah, defaults to Yule Walker. And here we have, so what are we doing? Well, it talks about the AR model here. It centers it by M, the mean, and then it fits P parameters. Notice that it's subtracting M from every piece, which is centering the process. And it says that AR is actually just a wrapper for these other methods. And let's see if it's going to tell us what they are. Oh yeah, so first of all, the AR function is not just going to fit an AR model, it's going to fit a lot of them. And it's going to use AIC, a standard model selection criterion, which you probably saw, especially if you took regression with me, then you would have seen that. Because we talk about it when we do model selection and specifically variable selection in linear regression. In this case, what we're doing is we're going to be using AIC, I guess. Well, it says true. We'll see. I'm not sure. Maybe there's a way to change it, but basically it defaults to using AIC to select the best model. Now, it has a couple little things where it says MLE performs true maximum likelihood estimation. I'm not sure exactly what it means by true maximum likelihood estimation. But yeah, I was hoping it would give more information on the actual methods. AR Berg, it says, allows two methods to estimate the innovations variance, which is just the variance of like the noise process here. One is based on an algorithm that we haven't talked about yet, but we will talk about. And method 2 is the mean sum of squares and a forward-backward prediction. So basically, in summary, fitting these things is not straightforward because it's actually also a big linear system of equations. And if you can ever avoid actually doing a matrix inverse, you probably should. And what we're going to learn about later is that even solving the Yule Walker equations, you don't have to necessarily invert a large P by P matrix. Now, okay, if P by P is not that big, then who really cares? But still, it's worth taking note of. Anyway, I'm going to stop meandering around. Let's see what this function can do, right? I want to see what it can actually do with some data. So let's give it white noise. And what does it do? All right, order 0, we did it. And it finds that the estimated sigma squared variance is a little bit less than 1. The answer is supposed to be 1, so it's pretty close. I think that's a win. And let's try AR1. All right, so it got the coefficient pretty close to 0.7. Didn't quite, I mean, it's a little bit higher, but it's within sort of the error. And it did get a pretty good estimate of the noise. I wonder what would happen if we gave it an MA1, right? It's meant to only fit autoregressive processes. So what happens if we do MA1? Wow, that's a lot of coefficients. So it actually gave us a bunch of different coefficients here for our MA process, which seemed to be decaying towards 0 fairly quickly. What in the world happened here? 7 kind of got, well, that's no good. Let's see if we give it a little bit more room. There we go. That just looked odd. Okay, so we notice a couple things. One is the sign is flipping, and 2 is that the coefficients seem to be roughly going to 0 in magnitude. Okay, they jump around a little bit at the end, but at least for the first bit, they're kind of decaying. The first one is kind of close to 0.7. The next one, kind of close to 0.7 squared, which would be 0.49. And hey, I wonder what 0.7 cubed is. I'm pretty sure 7 cubed is, was it 240? Well, we'll just do it. Oh, 343. Okay, so this isn't quite 343, but it's looking close. Statistical error and all that. And what's 7 to the 4th? Oh, well, 0.24. Okay, so that's kind of tracking. And if we do this to the 5th, I think we're at, 168. Well, this is 159. That's pretty good. What I'm trying to get at here is that we actually have a geometric decay. The idea is that if you recall that if we have an AR process and that AR process is causal, then we can write it in as a linear process. A linear process is an infinite sum of white noise terms going into the past. So it's kind of like an AR process is an infinite MA process, right? And the reverse is kind of true too. Remember that if we have an MA process that is invertible, that means we can write it as an infinite sum of some coefficient times xt, where xt goes into the past. So what we actually have here is we're showing that if we try to treat an MA1 process as an as an autoregressive process, what we get are coefficients that will geometrically decay to 0. They have to have some nice fast decay so that they're summable. Absolutely summable. I think it's absolutely summable. At least square summable, but I think absolutely summable is what we want. Regardless, it's geometric. It decays really fast, so you can definitely sum these things up. But where was I? Yeah, the point is that you can treat an MA process as an infinite AR process, and you can treat an AR process as an infinite MA process. So if you try to fit one to the other, you probably get something that looks like this, where it just picks a really big order and fits as many coefficients as it can. Because in some sense, every coefficient is non-zero, but eventually the value of the coefficient is so close to 0 that the noise overwhelms it. So it's kind of a neat thing to see that happen. And we still got a pretty good estimate of our variance sigma squared. Anyway, let's see if it does a good job with the AR3 process. Okay, so it almost did. It gave us an AR4. So can't win them all, but it did get the coefficients pretty close. It found my 0.7, my minus 0.4, my plus 0.2. This one's supposed to be 0. Again, can't get them all every time, but it did do a fairly good job, and it just decided that this should have an order 4 based on the AIC criteria that it is using, which is kind of behind the scenes. I think if we fit this, if we save this off, we might be able to look at more information. Because if you notice, the fitted thing is not just the model, but it'll give us a value for like the AIC. So presumably what this is telling us is the AIC, I guess, normalized at this one. So you can see how much, I guess, worse every other model is doing. So 3, the third order, and the 5th order are not much different than the 4th order. But you can see like a second order process has a much higher AIC. 6 and 7 start to get higher as well. So you can use that to kind of gauge that. Remember, AIC is just telling us what the best model is with respect to AIC. If you have two models where the AIC is really close, okay, one might be a little bit smaller than the other, but if it's not a big difference, then the models are pretty close and pretty equivalent. So you have to remember to kind of think on your feet a little bit when you do this, right? We don't want to restrict ourselves to say, it has to be 4 because that's the smallest AIC. Well, 3 and 5 also had kind of small AICs too. So they'll probably give you a very similar fit for the number of parameters. Anyway, let's see what else we can get out of this thing. So we have all of that. I'm not sure if there's anything else really interesting. We can look at the residuals, which would be nice because we can take the residuals and plug them into some of the things we looked at last time to see if our residuals look like they are uncorrelated. And if our residuals are uncorrelated, that's more evidence that we have a good fit to our model, right? We can do that later. I forget if there's a summary command, so let's just see if it does anything interesting. Sometimes in R we get nice summaries, so nope, it's just going to tell me it's a big list with a bunch of junk in it. So, they never implemented that, but that's okay. Oh, and we have one more to do, which is fit an AR model to my ARMA 1.1. So what do you think is going to happen here? Right, we have the AR1 piece, but we also have an MA1 piece. So in a sense, the two are going to combine. And what we should see is something very similar to fitting for the MA piece, but we're going to have I think they should add together if I'm doing the math in my head correctly. So the first coefficient, I would guess, would be around a 1.4 if you have 0.7 plus 0.7. Unless the two things, no, I think that would actually make sense. Unless they cancel out. I forget if there's a minus sign in there. Let's just see what happens. I overwrote my other model with it. No, it was 1.4. Good, my intuition was correct, which is now we actually have something about 1.4 here for our first coefficient, but we still have that geometric decay being realized as we move further out. So again, when you see something like this, like an AR process with a very high order, you have to ask yourself, is this an AR process with a high order, or is it just an ARMA or an MA process with a low order, right? It could very well and often is the latter case. But this AR function is only fitting AR models, and that's why we might end up with lots of coefficients. So it is something to be aware of. In practice, you're probably just going to use something like auto ARIMA to fit an ARIMA model to your data. It's faster and it fits many more models, but it's still good to know what's going on here. And once again, it does a really good job at estimating the variance, which makes me think it's probably going to do a good job at getting the residuals. Let's check the residuals. Why not? Let's see what they look like. So I think I saved this already, but let's go back to AR3, and maybe we'll do ARMA 1.1. So I'm just running on the fly here. Let's see what happens if we run our box test. So what we can do is we can do MD AR3, which is the fitted model for the AR3 process. We can extract the residuals from it, and now we can run this, but I think what we need to do is identify that we actually fit some parameters, so we have to subtract those degrees of freedom. In this case, I believe it fit 4, if I recall, right? Because it was an AR3, but the AR function decided I'm going to fit 4 parameters, so there should be 4 here. Unless there's one for the mean. We'll just stick with 4. And all right, that did not work at all because I got a negative 3 degrees of freedom because I forgot to change the lag. Rookie mistake, right? So if we change the lag to 4, well, now I have 0 degrees of freedom. That's no good. Yeah, I changed the lag to 5, now I have 1 degree of freedom and a very uninteresting p-value, which is telling me that, yeah, we probably have uncorrelated residuals. Now we can, if I remember is this going to do it for me? Yes, excellent. Okay, we can run either test. We still get nothing that interesting out. I could bump up the lag to something crazy like 20, and yeah, now we just have an absurdly high p-value, close to 1. So yeah, nothing interesting to see here, but we don't see, at the very least, if we try different lags out, maybe ones that are more sensible, we don't see any significant p-values here. So it's a good sense that we actually have a good fit for our data. Even though it's the wrong order, it's an AR4, whereas we know the answer is an AR3, it's still fitting the data well enough that the residuals look like they are uncorrelated, which is what we want, right? We want our residuals to look like white noise, uncorrelated white noise. For fun, why don't we see what happens with that MA, or let's do the ARMA because I already saved it. If we look at the residuals for the ARMA, now in this case, we have to consider the fact that we fit, I think it was 11 coefficients. Let's go back up and find it. Yeah, it fit 11 coefficients. So we have to subtract 11 degrees of freedom, which means let's bump this lag up to 12 and see what happens. And okay, yeah, we still get a insignificant p-value. That's good. We could try a few more just to see what happens, but nothing seems that exciting here. So that's good. That means that even though we fit an AR process to an ARMA 1.1 data set, we still get a good fit. And it's because if we actually wrote out that AR process, we would realize that it's really close to an ARMA process mathematically. Because again, the coefficients of the ARMA process as written as an AR process will go to 0 fairly fast, which means that we actually have something we can work with here. Now, yes, we have lost too many degrees of freedom than we should have, because we should only be fitting 2 parameters, one for the AR and one for the MA. Instead, we fit 11 parameters for the AR and 0 for the MA because it doesn't fit MA. But yeah, so that gives you an idea of what the AR function does. But there's one thing we didn't talk about yet. Well, I kind of talked about in the beginning, but we didn't try, which is that the AR function defaults to Yule-Walker. But we might want to know, well, what happens if we change that? So why don't we try that? Again, fitting an AR3. So again, if we try to fit this AR3, or fit an autoregressive model to an AR3, to our AR3 data, we get something that looks like that with our order 4 autoregressive process. But this is the Yule-Walker equation. I wonder what would happen if we change this to MLE, which is the other method we talked about. And okay, it did basically the same thing, but if you notice, the coefficients are slightly different. Now they're different in like the thousandth and the 10,000th place. So, okay, they're not that different, but the point is that they're slightly different, and they're slightly different based on the edge behavior. So because this is an AR4 process, I guess that means that it's going to be the boundary conditions on the first 4 and the last 4 data points. It gives us a very slightly different estimate for sigma squared, but again, nothing noteworthy, nothing really that noteworthy different. But we could try some other ones just to see what happens. I think OLS. Oh, so OLS went a little bit crazier and decided to include lots more parameters. That's kind of noteworthy. It decided it's order 7, but parameters 5 through 7, especially 7, are all quite small. So that one is, suspect, but that's okay. We can do Berg. Berg gives us, I'm not actually sure what Berg is doing. I should probably look that up in the documentation. I think they cite, I think I saw before that they cite a paper or something here. Or, oh, Berg is, okay, yeah, doing something with the Levinson-Durbin recursion. regardless, we're getting something that is, again, extremely close to the other ones like MLE and the Ewell-Walker equation, which I think just fell off the top of the page. So let's do it again. Yeah, so we can look at comparison-wise. So again, they're all kind of doing the exact same thing. And you see this a lot in statistics where it's, oh, look, we have 4 different ways to fit this model. They all kind of give you the same answer. So, okay, there's nothing too exciting going on here, but it is worth noting what is happening here. And yeah, maybe you might find a situation where you actually get some significant difference in the model fitted. Now, thus far, I usually have not been able to find anything like that, but you never know. Maybe for the MA model. Why don't we try that before we go back to the notes? Ewell-Walker gives us a 9th order autoregressive process. MLE gives us a 9th order autoregressive process. I think OLS sometimes does weird things. This one gave us a 6th order, so it actually gave us fewer terms this time around. So yeah, that's something to just be aware of. Again, the other thing to note is that most of these models are so close to each other that even if you have some extra terms that are extremely small, because the coefficients are so small, they're not going to make a huge difference in the fit. You're probably in all these cases going to get decent residual testing with things like the box test function. So overall, yeah, you could probably just use the Ewell-Walker equation. I don't have a good reason to suggest that you use one or the other, but it's good to know that they're there. Anyway, we're going to jump back into the notes now, because if you notice, there's something else here. The predict function, because we can also do prediction, or what they like to call forecasting in time series. But we don't know how to do that yet, so we should probably jump back into the notes and write it all out. And now we're back in, well, not RStudio. We are back in OneNote, where we can go through our notes and try to work this all out mathematically. So last time, again, we talked about this. We did estimating the coefficients. We ended with the idea of MLE. So I did want to mention one thing. Last time, we did Ewell-Walker for ARP, and we did MLE for AR1. And we showed that at least when P is equal to 1, the answer you get out is really close for both of those methods. And we just saw that in RStudio, that it is in fact the case. Now, the one thing I wanted to note, we can also do MLE for ARP, as was just done at least in R, but it's really messy and I'm not going to write it out. But the equations are messier. Briefly, though, I did want to point out that if you recall, what we did last time was we wrote the joint density function in terms of a product, not n, but t, the product of conditional density functions. So we started off with x1, and then we had f of x2 given x1, and so on, all the way up to f of x capital T given x capital T minus 1. Well, for ARP, we do the same thing, but we would need to condition going back P. So we'd still have an f of x1, and then we'd have an f of x2 given x1, but then we'd have an f of x3 given x2 and x1, assuming that P is at least 2. Otherwise, we'd just be in the same case we were above. And going forward with this very large product, what we would have is f of x, I guess, P. Well, it's pth order. So I guess it would be P plus 1 given x P through x1. And then the next thing we would multiply by would be f of xp plus 2 conditioned on xp plus 1 through x2, and so on all the way up to f of x t conditioned on f of t minus, or xt minus 1 xt minus p. So again, this just kind of hints at the thing that we can do everything again. Everything becomes a little bit messier. And now when we do a conditional sum of squares, we would need to condition on the first p observations. So the bigger the model, the more observations we have to condition on in order to sort of fix the maximum likelihood equation. Or just solve it, I guess, non-linearly if that's easy or not. To be honest, I'm not actually sure what that AR function is doing when I type in MLE. Is it doing the MLE with the unconditional sum of squares, or is it using the conditional sum of squares? Might be worth digging into the documentation or the code itself to find out. But yeah, I'm not actually sure off the top of my head. So maybe we'll leave that for a future investigation when we jump back into RStudio. But for now, we're going to move on to the next section, which is forecasting for ARP. So we want to do forecasting. That is, we want to predict, right? Because very often in time series, whether it's climate data, whether it's financial data, or whether it's something else, COVID data, for example, you kind of want to fit a model, but you really want to know where's that model going and what can we predict. So how do we do prediction in this case? Well, the problem at hand to solve is given x1 through xt, we want to predict, i.e. forecast, as they like to say in time series language, well, future values like xt plus 1 through xt plus m for whatever m is. So first of all, let's just assume xt is stationary, but not necessarily an AR process. So we just have some stationary time series process. And what we want to do is we want to try to see what happens if we use past values to predict future values. So if that's the problem, then I guess the solution is use past to predict future. It's a good idea rather than going backwards, though we will talk about the idea of backcasting, which is using the future values to forecast into the past. That's actually a thing, and we'll talk about it later. Not yet, though. That's going to be a future lecture. So that'll be a little teaser for a future video lecture. But anyway, we want to use the past to predict future values. And we're going to do via a linear model and least squares, because it's often always least squares in statistics, at least in undergrad statistics, and very often outside of undergrad statistics, you're often always doing least squares. So what we want, i.e., we want something that's going to look like, well, x hat capital T plus m. M could be any value, 1, 2, 3, whatever. And what we want to do is we want to predict it based on, well, the entire, not equals, the entire data set. So we have A naught, and then we have little t from 1 to capital T, AT, XT. So in this case, we're using a linear model, but we're considering the entire time series. which means there's a ton of parameters here. There's t, which could be big, like 500 in my example or more. And then there's an a naught, which is just going to be like an intercept or a mean term. But the idea is we can do that, right? At least mathematically, we can write that down and see what happens. So let's see what happens. Well, what we want to do is basically to get the AT, we'll say, the AT hat for t from 0 now with the intercept term up to capital T, we solve the following least squares problem, which is we want the argmin for the vector a naught through a capital T, which is going to be some giant real valued, I guess, t plus 1 vector. And what we want to do is we want to minimize, well, the squared error, because, like I said, that's what we always want to minimize. Almost always, it seems like in statistics, is let's minimize the squared error and see what happens. Well, to write it all out, 1 AT. All right, so we have that. And yeah, we're going to just take derivatives and try to figure out what we need to solve, right? Because what would you do in this case? Well, I would take derivatives with respect to the parameters a naught through a capital T, and I would set them all equal to 0 and then solve a big system of equations, right? To try to find the minimizer. Sorry, getting a little hot, so I thought we'll get rid of the sweatshirt and continue onward. So, what are we doing? Well, first, we would want to take a derivative with respect to a naught. And what does that give us? Well, if we take the derivative, and we're going to just swap derivative and expectation, because, okay, the integral makes sense, it works, it's, all that stuff's good. So what do we do? Well, when we take the derivative there, I'm just going to write it out here. What we would end up with is still an expectation, but what we want is we want 0 is equal to the expected value. And then if we take the derivative on the inside of the expectation with respect to a naught, well, we're going to get a 2 because we take the derivative of a quadratic, but nobody really cares about the 2. And in fact, we don't really care about the minus sign either, but I will write it there just for consistency, or maybe not consistency, but to be precise and to make sure nobody gets lost. Anyway, we take the derivative, the quadratic goes away, and we're left with just this. All right, cool. So we have an equation to solve. Well, kinda. Yeah, I guess I can write it more simply, though. If we note that we can actually write this whole thing as x hat t, because, no, t plus m, sorry. Because this, no, capital T plus m. Because this expression is going to eventually be the estimator that we want. And just to keep it a little bit cleaner, we can just rewrite this simply as 0 is equal to the expected value. Again, I can divide by -2. It's just a coefficient. And ultimately, I just want to find a root for this thing. So what we end up with is just x t plus m minus x hat t plus m. All right, so that looks a lot cleaner. Now, what would happen if we did the same thing, but we took the derivative with respect to a1? Well, almost the exact same thing happens. What we would get is we'd have our -2, sure, of course. We'd still have an expectation here. But now when we take our derivative, well, a couple things happen. We get the same thing on the inside of the square, which is the xt plus m minus x hat t plus m. But when we take the derivative of the inside term, right, chain rule, when we take the derivative of the inside term with respect to a1, we don't just get a minus 1 out, we actually get a minus x1 out. Oh, I lost the plus sign there. So we actually get an x1 here. Okay, so that changed things slightly. And of course, this minus 2 is kind of irrelevant. So we can just kind of cross it out. And the same with the minus sign here. We don't need that. Okay, so what if we went forward? Well, every subsequent term is going to look more or less the same. We can actually just take this all the way down to our final derivative, a of capital T, which is going to look like the expected value of xt plus m minus x hat t plus m x capital T. Okay, so now we have well, it looks kind of like a big system of equations, but we have to figure out what happens now when we take these expectations. Well, two things happen. In the first case, so let's start with this case. And we note that in this case, we're just taking the expected value of xt plus m and x hat t plus m. So what does that mean? Well, what this means is that we have to have the expected value of xt plus m has to equal the expected value of x hat t plus m. So that means that our estimator, our least squares estimator, or I guess our least squares predictor, I should say, it's technically we're doing prediction here, even though it's very close to the estimation that we did last time. The predictor that we have here has to have the same mean as the process itself. Now the process is stationary with mean mu, so that means this whole thing has to equal mu. All right, and therefore, if we recall that x hat is actually this sum up here, this linear combination, that means that we would have mu is equal to a naught, plus the sum t from 1 to capital T of at. And what happens when you take the expectation of all these xt's? Well, they're just mu because it's a stationary process. Remember, I said we don't have to assume that we have an autoregressive process, but we are assuming we have a stationary process, because what that means is we can rearrange the terms and say that once again, another therefore, we find that a naught is actually going to be mu of 1 minus the sum of all the other terms, or the other coefficients, I should say, at. Okay, so what does that give us? Well, once again, I'll say this means that, I guess I could just keep writing therefore, but kind of get tired of writing ... over and over again. So this means that if we actually plug this in, we end up with something that looks like x hat capital T plus m, our predictor for the, I used little t there. It should be, I think, big T for consistency's sake. I need to go back and change that. What we end up with here is basically this thing. A t, and then we have x t minus mu. Okay, and what we're basically doing now is we have, this is a mean zero time series. So what happens is the estimator that we would have for the mean, or for a naught, basically subtracts mu from all of the terms, which means we have a mean zero time series. And furthermore, I can actually just turn this into a minus sign and this into an equal sign. And now I have that the left-hand side is also mean zero, because as we said, the mean of my predictor has to equal the mean of the process itself, which is mu. If I have a least squares predictor, or estimator, predictor, sorry. I always want to say estimator. But so what does all this mean? Well, it means, well, like what I like to say all the time, which is just assume the mean is zero and get rid of it. Therefore, we can just center the process about x bar and assume going forward in the sequel, as they like to say, but I always found that to be such a strange term to use. So we assume going forward that xt it has or is mean zero. So basically what I'm saying is, okay, if you actually do this, you just estimate the mean as you always do by summing up for a stationary process, sum up all the data, divide by the total, then you take x bar and you take your time series, you subtract x bar, it's now mean zero. Good stuff. And we can proceed with all the more complicated bits. So now what we're going to do is we're going to specify things yet again, because again, it's a lot easier if we work, well, if we try to do, say, what they would call a one step ahead estimator or prediction. So let's try that. And as I read my notes, I realize they're riddled with typos and syntax errors, probably because I wrote these while stressed out during the first COVID lockdown. So I will go back and try to fix those. And if I forget, please remind me at some future point if you see those typos still not being corrected. Anyway, what do we have here? Well, returning to the other equations above, what do we have? Well, we have that 0 is equal to the expected value. In this case, we're going to say let m equal 1 for what is coming next. This is what they would call the one step ahead prediction predictor. Oftentimes they like to look at things like the one step ahead prediction error, which is like, as you go through your data set, how well are we predicting the next day from the previous time points? But at this point, we're just going to try to predict the next time point, which is going to be capital T plus 1. So we have x t plus 1 minus x hat t plus 1 multiplied by x1, and that's supposed to be equal to 0. And let's do it again for the next one, which is the expected value of x t plus 1 minus x hat t plus 1, and now we're multiplying by x2. And we can keep this going until we get all the way down to the expected value of x t plus 1 minus x hat t plus 1 times x capital T. And now we've run out of data, right? We went all the way from 1 to capital T. Now, if we stare at these, we might realize, well, wait a minute. If I'm taking the expectation of the product of x at some time point and x at a different time point, that's an auto covariance again, right? Auto covariance, like I told you, all of time series, just auto covariance. Don't even worry about anything else. That's a lie, but it's like 90% auto covariance, not 100%. Anyway, yeah, so what does that mean? Well, if we do this and we just basically take the expectation with respect to everything, then what we get is we get a kx at lag t for x1 times xt plus 1. And then in our summation, we end up with something that's going to look like t from 1 to capital T of a. Did I switch to alpha, or am I keeping it as a? We're going to keep it with a, even though I think I may have accidentally switched. Oh no, I was using alpha the whole time. I just wasn't reading carefully enough. Need to get my prescription updated. That's okay. It doesn't really matter. They both look the same. Anyway, we have an xk, and then we're going to have little t minus 1. Because remember what x hat is. X hat has fallen off the top of the page. But x hat is going to be the sum t from 1 to capital T. So if I were to take this thing and multiply it by an x1 and then take an expectation of that thing, then, well, what's happening? I'm going to have, well, a1 times the expected value of x1 times x1. That's just the that's the variance, the auto covariance at lag 0. Then it's 2, 2, and 1. Well, that's at lag 1. And then 3, 3, and 1. That's at lag 2. And so on. So what we end up with is something that looks like this, where I just have a long string of auto covariances being summed up with various coefficients. If we do that for the second one here, well, now I'm not going to get a t. I'm going to get a t plus 1 minus 2, which is a capital T minus 1. And now things get, oh no, it's fine. We can just write this simply as t, and this is now going to be kx t minus 2. And I'm going to say recall that kx of minus h is equal to kx at plus h by symmetry. So I don't have to worry about shoving an absolute value in there or anything. When little t is equal to 1, I'd have kx at minus 1, but that's the same as kx at plus 1. So it's good to remember that for what's to come when we write this as a linear system of equations. But for now, it doesn't really matter. Okay, and what's the last one? It's always good to do at least the first and the last, so we know where we're starting and where we're going. Well, now we're going to have a t plus 1 minus t, so the lag is just 1. And in this case, we're going to have a t from 1 to capital T, and we're going to have it's going to be little t minus capital T, but all of those are going to be negative or zero. So you can actually flip it by multiplying by minus 1, and we can write capital T minus T. I'll say, or just to be clear, we could write it like this, but again, symmetry doesn't matter. Multiply by minus 1 as many times as you like, but after 2, it's sort of pointless. So now we have a giant system of equations. Cool. What does that mean? Well, that means what we're going to do is, if we identify the fact that we basically have we have a 0 vector here. All right, so what do we have here? Well, what we have is a big system of equations. The first thing we're going to have is a big 0 vector. Actually, we'll write it out like that. And this thing is going to be, we're going to have a big vector here of auto covariances from capital T all the way down to 1. Then we're going to subtract from that. Well, what happens when we have a big sum like this? What we have is a matrix vector multiplication. So first we're going to have a matrix. That matrix is going to be a big matrix of auto covariances. And then the question is, did I actually index this the way that I want to index this? Let's see. Well, when t is equal to 1, this is going to be 0. And then in the last case, when t is equal to capital T, it's going to be 0. So yes, everything looks good. And I'm going to get something that looks like this. All the way down the diagonal at the bottom here, we're going to have a kx at lag t. It is t, right, and not t minus 1. Nope, I'm wrong. It is t minus 1, or my danger sense was working, where I'm like, wait, we're starting at 0, so we probably need t minus 1 there. And then over here, of course, we're just going to get a kx 0. And up here, we'll have another kx capital T minus 1. So here's our giant matrix. It does have common diagonals, so that's always a nice thing to note, that every diagonal is fixed. We start off with the main diagonal being the variance. Then the first off diagonals are going to be the autocovariance at lag 1, then lag 2, lag 3, lag 4, all the way up to lag t minus 1. Again, we don't typically want to go that far out computationally, but mathematically, we're all still good here. If we somehow knew exactly what the autocovariance was for every possible lag. Estimating it that far out is a bad idea, but we'll worry about that in what's to come. And we have a vector of coefficients here, up to capital T. So if we rearrange the equation, if we call this, we basically get vector k is equal to matrix gamma, which I'm going to call it gamma again because it looks basically the same as what we saw in the Ewell-Walker equations, with one noteworthy difference. And I'm just going to say A. And there is our nice system of equations. So idea is that this is just like Ewell-Walker, but gamma in Ewell-Walker was P by P. Okay, and P is probably not that big. Again, you're not going to want to fit like a 100th order autoregressive process, right? You're fitting like a 4th order or like a 11th order like R did. So 11 by 11, not a big deal. But now, whereas this gamma is T by T. Now that's kind of a problem, right? We don't want to invert that because that could be, well, in my R example, 500 by 500. But you could easily have it even more if you're doing even faster or more highly observed data, right? T can be quite large. We're not going to want to invert that. Furthermore, we don't actually have the autocovariances kx. We would have to estimate them k hat of x. And remember, the further out you go lag-wise, the worse your estimation gets. And if you're trying to invert something with a bunch of shifty estimators that are kind of noisy, there's going to be a lot of numerical instability in this, and you're going to run into some trouble. So yes, this is roughly what's going on. Mathematically, I can write it down as a beautiful linear system of equations. In practice, we don't actually want to solve this thing. But what could we do? Well, let's go a little bit further and at least study this. Yeah, based on how much time I've been talking already, what we're going to do is we're going to finish our study of this in a mathematical context. And then in the next lecture, we're going to talk about how do we actually work with this, because that thing looks pretty cool. It looks very simple, but we can't work with it. Too big. It's a nasty system of equations. So with data, it's not going to work. We need something better. But that doesn't mean that we can't keep pushing ahead mathematically to understand what's going on. So effectively, yeah. So from this, we can write A, the coefficient vector is equal to gamma inverse K. assuming that gamma inverse exists. It probably should if you have a reasonable time series process, but yes, you could write down some crazy ones that have, I guess perhaps the easiest one would be if the process was constant, which would be really stupid, but yeah, you could have a constant process, in which case, I guess all of the auto covariances would be the same. Everything would be perfectly correlated. So that would be, troublesome to say the least. And then, things would go awry. But forgetting all numerical stability, singular issues, assume this exists, then we can write down our coefficient A. So that's nice. Then, therefore, our one step ahead prediction is x hat t minus 1. Well, what was this, right? This is just going to be the dot product of the A vector with all the previous x's, x1 through x capital T. Okay. Well, we have A as gamma inverse K, so we can actually write this, well, in a little bit of a funny way, because when you do the dot product, this is actually A transpose X. If we treat X as the vector of values, the time series from 1 to capital T, then what we're going to end up with is something that looks like K transpose gamma inverse. Again, gamma is symmetric. Its inverse is symmetric. I don't have to throw a transpose in there, which makes everything look a little bit nicer. And there we have it, our one step ahead prediction estimator, assuming that I had access to, well, K and gamma. So in this case, we can actually compute the mean squared prediction error, which is nice. The mean squared prediction error, I will say based on kx, not kx hat, right? Because ultimately, when you estimate the autocovariance, you're going to have more error or more sources for error. In this idealized setting, I'm just imagining that somebody, reached into their pocket and handed you the autocovariance and said, here you go, this is the autocovariance, go have fun with it. And then you can just plug it in and run with it. But that typically doesn't happen. But we can still mathematically consider what this would be. Our mean squared prediction error, if we go all the way back to where we started, is going to be the difference between xt plus 1 and our predictor. Our predictor here is going to be k transpose gamma inverse x vector squared. All right. Well, what happens when we expand that thing? Well, when we expand that thing, what do we get? Well, we're going to get xt plus 1 squared. We're going to get, all right, we're going to get a couple things. It's going to look a little bit messy, but these things, even though this is a vector times a matrix times a vector, it is just a real number. So we can treat it as a real number, and we would get the cross term here, which would be 2 k transpose gamma inverse x, and then multiplied by xt, with the somewhat annoying notation that x here is a vector and x sub, t plus 1, capital T plus 1 is just a single value, a real number. And lastly, we're going to get this thing times itself. But when you multiply one of these things by itself, you have to, you have to transpose it to make it kind of make sense. So what we're going to get is something that's going to look like k transpose gamma inverse x. then the transpose of this, which is X transpose, gamma inverse, again, it's symmetric. I don't need to throw a T in there, K. All right, so we got that big thing. What can we do with that? Well, what we're going to do is we're going to go one by one and take the expectation of each piece. So we have 1 piece, 2 piece, 3 piece. All right, so what we have here is just the first term is really just the expectation of the process squared. It's the variance. It's the auto covariance at lag 0. That's easy enough. What happens to this next piece? Well, in this next piece, what we're doing is we're taking the first stuff is not a random variable. Again, because we're not estimating the auto covariance, we're just pretending that somebody gave us the auto covariance. So the only random bit is actually, if we erase this line, is going to be this last part that we have to take the expectation of. Now, the expectation of that is just going to be the expectation of x1 all the way to x capital T times x t plus 1. We already have that. That's vector k, right? That is exactly this vector k, except for the fact that, is it upside down? No, it's not. Of course not, because it starts, x goes from 1 to t. Therefore, the top auto covariance is going to be t, capital T, all the way down to 1. I wanted to make sure I didn't reverse the vector there accidentally. But we're good. We got that. And then the last one. And then similarly, the only thing we actually have to take an expected value of is this thing in the middle. Well, when you have x transpose, that looks a lot like a covariance matrix. In this case, it is going to be, right, every entry, maybe I'll write that off to the side just for clarity's sake. The ijth entry is what? X. Now I have to figure it out. I guess it's going to be x sub I times x sub j. So that's actually not that hard. I was just making it more of a problem than I thought. So I guess if we were to take the expected value of this thing, we end up with just the auto covariance at lag I minus j. Well, wait a minute. We've already seen that. That's exactly gamma, right? That's this crazy giant gamma matrix here, which is just saying I minus j is just saying how far away am I from the main diagonal. If I'm on the main diagonal, I equals j, the index is 0. If I'm 1 off, I minus j is equal to 1 or minus 1, doesn't matter. Because of symmetry, we get a 1, and so on. Yeah, so it turns out that thing is just gamma, and we end up with k transpose gamma inverse gamma inverse k. Then we can cancel out one of these gammas and gamma inverse. Well, the gamma with a gamma inverse. Then it turns out that the second two terms, they don't cancel out, but well, I'm going to write this as the variance of x t. Well, let's put cap. Yeah, I'll just write the variance of x t. It's constant. The variance is the same no matter where we are. And then we're going to be left with just a k transpose gamma inverse k. All right, so that's kind of a nice form. So this is for our one step ahead prediction. So what does this mean? Like, how do we interpret this, right? Because I'm writing this down so we can stare at it and try to make some sense out of it. Well, it says that the prediction error is the variance. That's reasonable. Right? It's saying, well, if I have to predict to the next point, we know what the noise is. The noise that's coming into play is that whatever the variance of xt is, sigma squared, or I guess, no, actually in this case, sigma squared would be the white noise variance. depending on the process we have here, the variance will differ. But it's just the variance. But then we also is the variance, but with a subtraction, which is this piece that I have to loop all the way around to point my arrow at, lest I cross the sentence. So what is that piece? Well, that piece is a big quadratic form of, I guess, autocovariances. So the point is that it's the variance minus the information gained via the data. So that's what that second piece is telling us. It's saying that the mean squared error is going to be reduced. It's going to start at the variance. And if the autocovariance, if K is just 0 everywhere, except of course at except of course for the variance, which is the autocovariance at lag 0. But for all positive non-zero, for all non-zero lags, if the autocovariance is just 0, the second term vanishes, and it tells us that our mean squared prediction error is just the variance, because it's kind of saying, you know what? That's the error you're going to get. You can't do any better than the variance of the noise process. But when the autocovariance vector K is not all zeros, then things get more interesting, because what that's going to allow us to do is it's going to reduce the mean squared error. And then you might be asking yourself, well, wait a minute, is that thing always going to be positive, or could it be negative? And the answer is yes, it actually has to be positive, or at least non-zero. So note that K transpose gamma inverse K is necessarily non-negative, because gamma is positive, semi-definite. This was something I think we talked about back in like the second lecture when I introduced autocovariance. I said, autocovariance is, positive definite. And it's like, okay, why do we care? Well, this is a good reason why we care, because now 10 lectures later, we find out that that positive definite, or just to generalize it, positive semi-definiteness, in case we have some stupid like edge condition, allows us to identify that the mean squared error, the mean squared prediction error, can be no greater than the variance of the process. And ideally, we'll be getting some good information from x1 through x capital T, and it will be reducing the mean squared error. So that's the idea. Hopefully it actually works in practice. We still have to figure out how to calculate all these things though, because I don't actually know what gamma is, and I don't want to work with a capital T by capital T matrix. But we're going to save that for next time, but we're not done yet. We do want to just point out that, let's see, what do we want to do? Yeah, let's look at the ARP process. Yeah, we'll just do that and then we'll end this. So as noted, we don't want to work with gamma being T by T. But if xt is an ARP process, remember at the beginning I said we want to do forecasting for ARP, but we're not going to assume we have an ARP process. We're just going to do least squares. Well, now let's assume that we actually have an ARP process. And what does that lead to? Well, what that leads to is that the then the one-step ahead predictor, let's say, is just x hat t plus 1, which is going to be the sum. Now I'm going to take I from 1 to capital P of phi I hat times x t plus 1 minus I. So t minus 1, t minus 2, all the way down to t minus p, where phi hat comes from the Ewell-Walker equations, where phi hats come from YW Ewell-Walker equations. So what we realize is that in this case, we're just doing the Ewell-Walker equation. And I mean, it probably looked really similar if you recall what I did in the previous lecture video. You would have seen the exact same matrix, linear system like that, but capital T would be replaced with just P, and it would make our life a lot easier. Whereas now we have a giant matrix that is capital T by capital T. So the point is, in summary, if we knew that we were had an AR process of order P, we could do our one step ahead prediction doing this method, which is equivalent to Ewell-Walker, and we only need the previous P observations. So again, like I've said before, if we have an AR1 process and I want to predict the next guy, all I need is the current guy. I don't care about the past. I just need the current guy. Now, okay, in practice, we would use the entire data set to estimate the parameter phi, but that's a separate thing. Once we have the parameter phi, we only need the most recent p-values. That is not the right way to say it. The most recent p observations, p-value, another thing, p observations to predict the next observation, and so on, which means that we can actually solve that system of equations very easily to get the answer that we want. But if we don't know that we have an AR process, then we can't just solve that system very easily. We have to work a little bit harder, and there are ways to do that thanks to people, not in statistics, but actually in numerical linear algebra, because it turns out that gamma is a very special type of matrix. It's a Toeplitz matrix, and lots of people in numerical linear algebra have studied these things. So we're going to study them too, but we're going to save that for the next lecture. See you there.